Hello guys. Today we are going to speak about hierarchical temporal memory. So, what is hierarchical temporal memory? Hierarchical temporal memory is an algorithm. It's a theory which proposes an algorithm about the working of the brain. So it was proposed by Jeff Hawkins. He's done research for over 25 years and started Redwood Research Center for Neuroscience and also a company called Numenta, who try to bridge the gap between intelligent machines and how the biological intelligence behaves. So they try to model the behavior of the brain to better understand how an intelligent system would behave. So the first thing is we see the Baddeley's model of the perception of the world down here, which shows that there are different regions within your brain that are specialized in perceiving different aspects of reality, like the sound through your hearing and through your vision. You see all the objects around you and how your immediate environment is set up. What are all the spatial features, as in how far, how near things are, all that, and all this composites together your view of the world. So in essence, each of these individual um, parts are performing a basic pattern recognition that is the same. It's going to be applied through across all your visual and audio or any other kind of sensory inputs. So the brain, so what is happening in the brain is the neurons, every neuron is picking up a particular pattern, and the pattern being picked up is like represented by the activation of the neurons. So when different patterns occur within that are picked up by your sensory regions, there are different neurons that get light up, which uniquely represent each of these events, so called events. You can call them as sequence of occurrence of patterns, of things that you define together as a pattern. So it is a same sequence that keeps occurring over and over again, which you will call a pattern, which is a generalized perspective on things. And the this theory is based on the working of the neocortex, that is the outermost part of the human brain. So there are many parts to the human brain, and the neocortex is the most very special part of the human brain, because it is what makes us unique from other mammals or reptiles. The neocortex of a human brain is six layered and much thicker than that of any other mammal. So there are more there are more hierarchical processing. So the hierarchy occurs from your sensory inputs to the top of your to the end of your neocortex. So the for first feed forward of all this input stream data is being picked up by your sensors, and it goes through a bunch of different parts of your brain, and ultimately all these sensory inputs end up in your neocortex, and they have different semantic meanings. So based on how these patterns are picked up in different combinations, there are some higher level understanding or grouping of these smaller patterns within different sensory regions to form higher abstract concepts. So when you start out by feeling an object, you by if you want to recognize a particular object like a mouse, there are various things that go into getting the abstract concept of a mouse. So one of the aspects is the touch sense. So you feel the object by running your fingers across the entire object, and you see how it changes, how its surface changes over time. So the patterns are distributed over time. So this sequence of these changes in this three-dimensional space is what represents the feel of the mouse. And you obviously know that when you click a mouse, it makes a unique sound that has been the same from the time people have made created mouse. So it's very recognizable. So you don't even have to actually look at a mouse. The moment you hear a click sound, which is at a certain frequency, you get a visual cue in your brain without actually having to see something of a mouse click. So this abstraction, this higher level understanding of things, making a model of the objects in your environment, is essentially what the neocortex does, and it uses something called as the cortical circuitry. So in the cortical circuitry, there are array of neurons that run from your sensory region to specific parts of your brain, which are in the neocortex, and they run through various parts of your brain. So if you take, for example, your eyesight, your eyes are made of retina and lenses. The main part here is the retina, which takes in the light, and it has some vague representation. You can call it a sparse distributed representation, in the sense within your visual space there is like a center of focus where you are actually seeing things. Like those are the places where the light coming in is more defined. You actually have more semantic meaning to the light that is coming in to the center of your retina than that compared to that of your outer regions of your sight. So this sparse distributed representation can be viewed as like uh, a representation of an entire room based on some abstract concepts like a question. So when you enter a room, you ask what is the shape of the room, and how many people are in the room, what is the time of the day, where is this room located. All these are different uh, features or semantic meanings that you will give to a particular sequence of inputs, so you can have a better understanding of these input sequence.
So, who drew this? Did it?
Yeah, I drew this.
Okay. So, can you quickly show the older slide?
Yeah.
Okay. So your definition of the sparse distributed representation might confuse us. So you will explain it later.
Yeah.
But you are associating semantics, like which objects are in this room, right? Mm-hmm. This is a semantic, but you are confusing. So semantics and sparse dense distributed representation has nothing to do with. It is a totally different concept. So SDR, we call SDR, is simply speaking, when you have a vector of 1000 dimensions, it means only, let's say, 12 of them, 12 is on and the rest is off, right? So because it's only 20, it's sparse and distributed, and it's a binary. So this is actually very big
change, big thing in terms of the how we represent concepts. So many people in this room, or I would say 99.9% of the AI or deep learning, so mainstream, all the world is working on the densely
Dense representation.
Yeah, dense representation. So dense representation is when you have a 100 dimensional vector, everything is a floating number like 0.9 to 0.023, things like that, right? So when you talk about neural net, almost everybody is using this representation, and there are not so many, there are few, but this is a very minor of the minor view. So you should know when you talk to someone and you do research and you mention this, chances are highly that the person you are talking with do not know this, right? So,
Can give an example of?
sure.
Yeah. So, let's consider the bit sequence 0, 1, 1, 0, 1, 1, 0, 1. So, suppose this is the dense representation. I mean, this we know according to ASCII standard it's M. It represents a particular letter. But if you take each of these individual bits, they don't represent this M. So this entire representation on the whole makes sense as M. But if you take away, like if you look at it bitwise, it doesn't make any sense, because you can just 1 with all other bits 0 is 1, or if all bits are 0, it represents 0. Its meaning changes. So this is the dense representation. So what is the sparse representation is, we take the same letter M, we have not just 8 bits to represent, but lots of bits, like suppose 1000 bits that represent the letter M. So how will this representation occur? So it's supposed to give features of the letter M. So M is a consonant. So there will be some bit that represents whether it's a consonant or a vowel, which will be a 1.
No.
Sorry.
You are confusing.
Okay.
You have to study more. You are associating too many. Just think of this is how you can build machines, and so then why this one is working well, this one is nowadays really popular, then why we need something like this?
So in dense representation, nowadays it's very popular because it's very case specific, in the sense that all the networks that like the algorithms that are built are used to find a specific type of occurrence. It's not learning a general overall pattern recognition, in the sense that so we have the RNN that can predict a sentence based on some input data. It can predict some sentences. So currently it predicts purely based on the representation, or how it has just occurred within the data set, but it's not keeping in mind how it has occurred over time, or over different combinations or what are all the possible ways it can occur. So it's not creating a whole probabilistic graph, but rather trying to find a random way of mimicking the same pattern.
Okay. I think you need to think about it a little more. So you are trying to associate functions, but they are every. Let's say you have some kind of classifier. You can build a classifier using both representation. The representation does not matter. The reason why they study sparse distributed representation is because this one is more biologically plausible. Simply speaking, if we look at our brain, it looks like this. We have, let's say, 1 billion cells. Only 2% of the cells are active at specific time, and they are changing over time, right? So this is how our brain looks.
You say about 2%? 2% of the
2%.
The entire
Yeah.
set of neuron.
Out of 1 billion neural cells, only 2% are active at specific time, right? So you can think of brain as a big bulb, and some of the bulb, 2% of bulb are flashing. So this sparse distributed representation contains a few characteristics that will be useful. I have just hypothesis yet, so I cannot guarantee, but probably this one will be easier for the one-shot learning. This is slightly
So one-shot learning is your hypothesis?
no.
One-shot
One-shot learning is a phenomenon. So let's say you have a mouse and play your music and apply electric shock, right? Just one time. And next time when the music comes, the mouse will not be very happy. He will be very scared. We can just do it one time and learn those associations, right? These are biologically observable phenomenon, and this dense representation. If you look at the history of the AI, there was a single layer, and then comes the multi-layer perceptron, which is a multi-layer. And I think it is this time when they adopted backpropagation as a way to train the neural net model. And this backpropagation model needs to be differentiable. To be differentiable, things need to be, how I say, continuous.
Online learning.
Yeah. So that is why this one now becomes a major history. But I think we are some kind, this HTM theory or Jeff Hawkins is some kind of level. He questions that this current approach is not right way. There is something wrong. So he studied it for more than 15 years now on his own money because he is really rich. He was
Palms Bro. He founded a company that basically made Palm tablet PCs. He was an electrical engineer, and because he knew the architecture of how a computer system works, he essentially understood that the whatever models, even though inspired by the brain, uh, due to the limitations of the understanding of the brain when these theories all that built up the MLP came up, the representation of the neuron itself was essentially wrong. In the sense, it was very simplified. And he, after you look at it and study about the actual working of the neuron, it's far more complex than what you would find in a neural network. So a neuron is actually having many connections with dendrites. There are proximal dendrites which get the inputs from its previous layer or from the sensory layer, and these neurons are arranged in a column and across layers. So the neurons can be connected with are always connected with the neurons within the same columns, and they also connect to neurons that are in adjacent columns or the columns that are surrounding this region. And that's how they are able to, so neurons that fire together work together. This is the basic working of the brain. So when input sensor comes in, based on which neurons are getting fired together and which columns they are in, new synapses connections forms to these. It's essentially a feedback system. So every time it sees a sequence of neurons firing over a period of time, it recognizes that this is a pattern, and synapses are connected to these neurons, so that when the same pattern occurs again, instead of it not knowing which neurons are going to fire, rather it will start predicting which are the possible neurons that will fire next based on the current input. So essentially, the brain is constantly running a predictive algorithm based on its previous inputs, and it is constantly checking whether its predictions are how accurate its predictions are, and based on the mistakes it has made during these predictions, the neuron connections are rewired essentially, and these new patterns are incorporated within the existing pattern. And there's something called as the synaptic decay, which is a parameter that just suggests how long you'll remember a pattern for, or basically a memory. Like it is a threshold that decides how wide, like how much of a percentage of occurrence of the same pattern should happen over and over again for the neurons to remember the sequence. So a sequence that the neurons have seen recently are more likely to be triggered in the same sequence than something that it has seen a while back. So based on the current input status, it is changing. So contrary to our previous approaches, where there was a clear training set, so you take all the inputs, you feed it to the neural network, and it like calibrate all the hyperparameters based on what you want to get out of this input as an output, and it will essentially it's a closed loop. So only based on these training sets you make all the changes, and then you test whether it's running correctly with the validation and the test set. But what this one-shot learning is a more realistic model of how we learn, because a brain doesn't have the time, or it doesn't go around gathering data and then running some kind of processing separately. Rather, as and when a new input comes in, it tries to incorporate it within the existing algorithm and tries to see how it can improve the prediction.
So so your seminar feels like a monologue,
Okay.
right? And you are pouring lots of information to the audience.
Mm-hmm.
But if you pour too many information, then actually it is difficult to understand or follow what you are saying. So even though you are saying a lot, actually audiences are not catching anything, right? And you are mixing the level of details.
Okay.
So when you are talking new things to people, you should begin with a high level talk, high level overview, and then go into the detail. But you are adding too much details into the introduction. So for audience it is difficult to understand what is the main or what is the detail.
Okay.
Because so I think let me do this seminar today,
Okay.
and you can prepare another seminar.
Yeah.
Okay.
Yeah.
I think this is a slightly theoretical seminar, so it might be too much for you to
Okay.
explain today. Or let me use your slide deck.
Okay. Actually, this is one of the main examples which would give a better insight.
So you want to try that?
Yeah.
Okay,
Let's try this example.
Yeah, let's try that. Yeah, let's see how it goes.
So here we have a representation of the sentence boys eat many cake. Bigger? Yeah. So here we have the representation of a sentence boys eat many cakes. So here we are trying to find sequences of occurrence of words, and these columns, each of the columns represent an this entire thing represents the word boys, and each column represents a unique occurrence of the word boys. So in your first sequence, since you have never encountered the word boys, all the neurons in this particular column light up, and in these three columns light up, and these three columns represent the letter boys, its first occurrence. Then eat is also occurring for the first time, and many and cakes. So these are the individual representations of each of these words in a sparse distributed form. So now we start analyzing. We first, when we encounter the word boys, we don't know what is happening. We just have this word called boys in front of us. Then we get the word eat. So we start within the within the columns that represent eat. We start selecting based on some criteria few of the neurons that will act as a representative of this occurrence, as in occurrence of eat after boys, this sequence. And then there is many. So when you come to the word many, now this is being represented with respect to boys and eat. So the neurons that get fired to represent the many in those columns are with respect to, so those are the cases when it is preceded by boys and eat. And cakes is the same. So that cakes gets lit up when there was boys eat many in front of the cakes. So this entire sequence represents the pattern of this sentence. And this is a, sorry?
So if it was a different sentence ending with cakes, the representation of cakes would be completely different?
No. So that is the next example. So there is another, so here we have eats and many are the same. Only pies and girls are different. So for eat and many, you have the same columns that represent the letter, right? But within that column, which cells fire that is what makes the difference. That is how you record the pattern of occurrence.
So the one with the dots are fired cells?
Yeah. So when you encounter the first letter girls now, right, you again don't know because you have never encountered the letter girls. But then again, eats is a familiar word, but it's occurring in a different context, right? So there are different cells that get fired within the column. So if you see the eats over here have different cells, the eats over there have different cells, but within the same column.
So are you saying like in our mind, in our brain, we have like place for every word?
Yeah. So this is only a four-layered like this is only one slice of a layer. So within a layer there will be many columns and many bits. So this is an abstract way of thinking of how we represent concepts in our brain. So if you want to understand a sentence, you try to see the sequence of occurrence of the words, right? So, and you need to recognize that there is something called as words that define a sentence. So each column will represent not each column, but a combination of few columns will represent a particular word. So when we come to the second pattern, we see that within the same column, now the context has changed. So we can compare only the eats and many. So this is for boys eat many cakes. This is for girls eat many pies. You can see how the same words are being represented in different patterns within the same column. So this kind of gives you an ambiguous view. So you could think of it as combination of different patterns. So within even when you encounter the same word eat, you want to know, like if you want to recognize a particular pattern based on which neurons get fired when you perceive the letter eat, you can make the prediction what will be the next, what this entire sentence is in context to. So if you just read the letter eat with this particular arrangement, you automatically now know that it is kind of representing the sentence girls eat many cakes, many pies. Because you already know when you previously encountered the pattern, those are the neurons that got fired. Right? So now you know that the possibility of this particular sequence representing that sentence is high. Because you have already learned the pattern. And finally we come to the difference. So up till here the sequence is the same. And this particular, the last letter, so when you start a sequence from eat many, you have this particular representation where it can be either or. You do not know which sequence it's representing, right? But once you get to the last word, now we are sure based on how the last word, what the last word is, or which neurons it is rather activating. You get to know that the first sentence represents the boys eat many cakes, and the second sentences represent girls eat many pies. Does this make sense?
Can you go over the last one and explain the difference?
Okay, so here, imagine that we just encountered, after learning the two patterns, we have encountered eat again. Now you want to predict what will be the next word. So with both the patterns that you have learned, you know that eat many are like in a sequence in both the patterns. So that is the common point. So it's easy for you to predict that eat and many are next to each other. So you'll predict that many is the next word.
Yeah.
So that prediction is right. Now you get to many. So once you get to many here, now you want to predict what will be the next word. It can either be cake or pies. Cakes or pies. So that is represented by this bottom part here, which is where the neurons are highlighted in blue, which is a combination of both the cakes and pies. So when you are trying to predict what will be the next word, you are predicting that both are a possibility because you have learned both the patterns. You are predicting now both are the possibilities.
Okay. Paul, can you explain why you learned today?
Sure. So we started off with why we are using hierarchical temporal memory and why we are moving from a densely represented vector to a sparsely represented vector. And the reason being is because it's more biologically plausible. Then we basically looked at how we could use the temporal memory algorithm and how the sparsely vectors are in layers of columns, and each column represents it could represent a word. Okay, so different cells get fired. It could be from different columns, and it depends on the pattern. So if there's a sentence and let's say 3 or 4 words, the third word could be based on the first 2 words. So different cells would fire depending on different sequences.
Okay, Aishwarya, can you explain what did you learn today?
About the temporal memory algorithm, I learned that there are separate representations in our brains for each word, but what neurons will fire in each columns would depend on the sequence that your brain is predicting.
Okay, Pamas? Or Paras? Paras? Yeah, what did you learn today?
It's kind of same as Surya's. The way the words occur defines the column, and well, the words define the column, and then the way they occur defines the cells in them, and how they can they can be used to predict the upcoming words.
So how do you learn that how brain updates its memory, its prediction? Like say it's kind of same as like neural network works. Like say based on the data, it updates its gradient descent, and that's what I understood most from his point that he said earlier. Like say, if brain prediction is wrong, then it tries to update its pattern sequence. Then on next time same pattern occurs, it will give you the accurate prediction. So that's all.
Sanjay?
So I understand the concept of the one-shot learning and the concept of the sparse distributed, which is, as Paul said, biologically plausible. And then in terms of this one, so basically our brain has a placeholder for everything, and once I see it for the first time, those placeholders, I don't know what you call them, but let's assume it's placeholders get activated, and if you see those words in a different way, then they will be activated in a different.
Okay. So, thank you, Sanas. You need to practice
Okay.
on the, and you do not understand the HTM yet.
Okay.
So, let's start. So, can you go to, let me finish here. So.
Yeah.
I have a question.
Mm-hmm.
You said the representation of the neuron is too simple in neural networks. What's the difference between the neural networks and...
Oh yeah, I'll explain it. Okay. So, let's say hierarchical prediction memory. And let's start with the hierarchy, right? So you guys have learned CNN or typical neural net, right? Things like that looks like this. So and you have learned that there is an input, and input is represented as a low level features, high level features, and maybe a category, right? This is how you run the neural net. Am I clear? Parents, do you understand what I mean? So, there is a hierarchy, and you can think everything as a vector. So, this input will be the vector, low level feature will be vector, high level feature will be vector, even category will be a vector. And here we use a sparse binary vector compared to the normal neural net. However, so let's say when we have the English word, there are characters like B, O, Y, right? And this will become a OI word, and this will become a phrase or a sentence, and this will be a paragraph, right? So even though he explained using a word example, it can be any level. Every level is working on the same principle, right? You should think it can be a word or it can be a character. And everything is just think of 100 dimension vector where only 2% of the bit is on, right? You can think of that, and it is changing, right? So each vector can be a character or a word or a sentence or whatever. Just think sparse SDL changing over time. And if we look at outside, everything looks same if it is a lower level or high level, because it's just vector changing, right? So here there is a two-part temporal association of sequence of these patterns. There are two parts: temporal association and spatial pooling. Spatial pooling is where we talk about how we can combine these lower level features to form high level features, which we will not talk today at all. We will not talk about the hierarchy. We will just think about this prediction memory or temporal association of sequence of pattern. It means think of this vector changing over time, and what you want to is, given this vector, predict this vector. Given this vector, predict next vector. Given this, predict next vector. So it can be in lower level, boy learns, things like that. In a middle level, it can be each vector can represent a concept. Or in a paragraph level, one sentence can represent one vector, right? So separate the level of detail from the this temporal prediction part. You are just predicting whatever pattern next.
So pattern would be a sequence of images, image to.
It can be an image. So if we think about the visual image, Sanas talked about the saccade, which is
The eyes moving.
Sanas, please. We are out of time. So you think you are seeing the high quality image, but what you actually have is you have a very high quality image sensor, which has a angle of about this, and very blurry sensor that has the angle of about this, right? And how you can get the high quality image? You move this high quality part very quickly, like 100 times per second. And in your brain, you build this kind of mental image of the static room with a very high quality view. So if you look at the sequence, you have a very small sequence. It's a 100 sequence per second, and each will be, for example, look like one eye, another eye, nose, mouth, things like that. So if you are looking at the human eye, you are very quickly scanning, and you can get the sequence of this, right? And this is represented as a sparse representation, and this can be predicted. So when you see two eyes, and when you move your eyes, you are expected to see nose, and if you go below, you expect to see mouth, right? So hearing, language, or vision, everything can be thought as a sequence of vectoral pattern. Am I clear about this? So the problem is how human brain can build a simple machine that can, given a sparse distributed represent, given a SDL vector, how it can predict next vector, right? This is the problem. It's the problem that HTM theory wants to solve. Actually, HTM theory is more than 10 years old, and there are many versions, and there are many failures too. So today I'll talk only about the temporal prediction memory, which I think is somewhat interesting. So in temporal prediction memory, they begin with one interesting observation. So can anybody explain how neural cell works? Neural cell.
So there is an axon, a center part,
Axon, yeah.
around which there are dendrites,
Dendrites.
so which are input input for the center of the cell, and then there
Okay. Sanas, you know, so others.
Okay.
Can anybody explain the working of the neural cell? You learned in the neural net class, or
You will get inputs from like
inputs, yeah.
And then it will have a function,
A function,
and it will give you one output.
one output, right? So given a few input, it generates an output. It's that simple, right?
The input activates the cells.
Yeah, input activates the cell.
So inputs are kind of sensory input like hearing or vision.
Yeah. So input can be anything, right? So you might think, oh, this is how cells look, but in biology, actual, if you look at the actual cell looks like this, and this is the like a cell body, and if there is a activation near the cell body, cell fires, right? This is why you think is like a outputting 1. If it does not fire, it is outputting 0. However, the cell does not have only 2 states, 1 and 0. From here, it is a hypothesis, but there are actually 3 states, right? Do you see here in violet part? So there are when other cells activate, then
It receives the signal.
pardon me?
It receives the signal.
Yeah, so what I mean by firing here means that actually there are other cells. So let's say here is a cell A, and let's say it has a, and let's say here we have a cell B, and let's say cell B fired, then there the output of this cell must have connection around this cell, right? The part that looks like this has a connection around cell A, and if this connection is close to cell body, if this cell fires, this cell fires, right? However, let's say we have a cell C, and it has a connection to the outside of the cell body, far from cell body. And when this cell fires, the signal cannot activate the cell, right? However, it can change the cell state to predicted state. Predicted state is like if you think about the electric voltage, let's say this is off, this is on, and the predicted state is something like this, right?
So it's like C is predicting that A will come next. C predicting A.
So let's say C, so A has come, so C has activated, A became predicted state, then let's say when cell is in a predicted state, you should think of cell competing each other to fire, right? So let's say we have a cell D, E, F, G, and let's assume D, E, F, G has all connection to the B, right? And when B fires, then all of this can fire, but because A was in a predicted stage, it has an advantage. It will fire first. And if A fires first, it blocks others it inhibits. It blocks others from firing. So A will become firing. So
Can we go over it again? This mechanism?
So
Is being in a predicted state anything to do with previous learning?
Yeah, predicted stage is essentially learning.
Okay, so I already learned that this sequence might occur, so that's the reason I'm predicting A.
Yeah, so once you develop, you experience enough of a sequence, you will become like a predicted activated. Then you think, oh, when C comes, A will become activated.
More likely.
Yeah, so from patterns from C to A can be learned. So let's say C has activated, A became predicted state, then somehow A became activated. And if it happens a lot, then the weight in the synapse changes such that when C comes, they expect A will come next. Right? Let's say this is also hypothesis, but we can think of some kind of column. Am I clear, Shade?
That's what he was explaining in the last difference. Right?
For me, he mixed a lot, so I'm not sure where he
No, I was just
explained.
trying to
Okay,
connect
there is
them.
one last take, the grid cell example.
Yeah. Okay. So these two structure is a difference from previous point neuron structure. So now they have two types of synapses. One that can be on like some kind of input to the system. The other, which is gives you context. We call this context. Which cells work, which signal patterns work before. So we can build a different structure of the neural cell that can represent this pattern. Do we have a question here?
So you could say that it's like the context is like a probability of.
No probability.
Okay.
Context is what has been before. If we are at the dinner table, what I talk when I say when we are eating apple pie, if I say apple, it might be a fruit apple, right? If we are talking about the new iPhone, then apple means Apple computer. So context is the how I say preceding signal pattern. So then how we can actually learn from if we have this interesting structure, how we can actually learn the patterns, right? That will be the most important part. And Sanas, you prepare one more seminar about how this structure can learn patterns, right? So, okay, thank you guys. Let's finish it here.
Yeah.